Section 5.3 Logarithmic Functions. In this section, we're going to take a look at log functions. We've been studying inverse functions, exponential functions to get to this point, because this chapter truly is about logarithmic functions and some of their applications. Okay, so let's get started. If you recall from the previous section, okay, we studied the exponential function. So let's write that down. We looked at f of x is equal to b to the x. Okay, two things I asked you to remember in that section. One was that f is 1 to 1. That means it has an inverse. And two, okay, we know the graph of the exponential function. It looks something like this. We have y is equal to b to the x. This point is always 1, 0. Okay, these are the two things we learned in the last section. Okay, so let's use these to study this section B. Log function. Instead of writing logarithmic function, I'm just going to say log function. Okay. Now, since the exponential function is 1 to 1, it has an inverse. So let's find it. So let's find the inverse of the exponential function. Okay. So let's do that. So here's my exponential function. F of x is equal to b to the x. Since it's 1 to 1, I know it has an inverse. So since it's increasing, it has an inverse. We switch. This is the same thing as y, so we switch x and y. So we get x is equal to b to the y. That's how we find inverse. And then the next step is to solve for y. And there's no way to solve for y algebraically that we've learned so far. So we are stuck because we know it has an inverse, so we should be able to solve for y. And to be able to do that, we're going to rewrite this y in this form. We're going to say y is equal to log of x base b. So that's what we're going to do. Okay. So that helps us solve for y, but in the process it introduces this idea of logs. Okay, so let me go ahead and define the log function. Okay, so before I do that, just so you know, one of the things students always ask me, what is a log function? One way to think about the log function, it is the inverse of an exponential function, because while trying to find the inverse of an exponential function, we were stuck, and we created this notion of logs to be able to solve for y. Okay, so here it is. And also from this point, if you recall, when we talked about exponential functions, we said also what? That b was greater than 0 and b was not equal to 1. So if b is greater than 0 and you raise it to any power, this number is always going to be positive, just so you guys know. Because if you take any number, raise it to whatever power you want, either negative power or any number to a positive power. Okay, if that number is positive, like b is positive here, this number is a positive number. Let me write it that way. So we have a positive number raised to a negative power, or a positive number raised to a positive power. Doesn't matter what it is, you're going to end up with a positive number in both cases. That means that tells me this x must be positive. So that's an important thing to note. It's never going to be 0, it's just going to be positive. Okay, so keep that in mind, because that's one of the things about logs that's different. Okay, alright, so let me go ahead and define it. If x is greater than 0, okay, and b is greater than 0 and b is not equal to 1, okay, then y is equal to log of x base b. This is called the base still. B was the base at the beginning, it's still the base. It's a base of the log now. Y is equal to this if and only if x is equal to b to the y. We were here and we got here. If and only if basically means this goes in both directions. If I have this, then I can write it this way. If I have this, I can write it that way. So here's a definition of log. Okay. Oops. So we call this the log function. So the log function, logarithmic function, or the log function, is f of x is equal to log of x base b, okay, where x is greater than 0, I already proved to you why, and b is greater than 0 and b is not equal to 1. So those are the requirements. So here's the log function. There are two things you should always take away from the log function. Okay, one is it is the inverse of an exponential function, and the other thing is you can see from here, and which is what we'll exploit quite a bit later. Anytime you're solving an equation, this is an equation where the unknown is an exponent, like y, because we're trying to solve for y here, remember that? You have to introduce logs. Somehow logs have to show up somewhere. So anytime the unknown is an exponent, you have to introduce logs to solve for that unknown. So those are the two things I want you to take away from this section. Okay, there's other very important things in this section, but those are some things that to keep in the back of your head for long term. Okay, alright, so now that we know what a log function is, okay, it is the inverse of an exponential function, and this is what it looks like, where b is the base and there are the requirements of b. Let me go ahead and graph the log function. Of f of x is equal to log x base b. So let's go ahead and graph this. Well, it shouldn't be that difficult to graph this. Why? Because we know that this is the inverse of an exponential function, and we already know what the graph of the exponential function looks like. So once we have that graph, we can just fold that graph over the line y is equal to x to get the graph of the log function. So let's do that. So here this is I'll draw the graph of the exponential function in green. So here's a graph of the exponential function. Y is equal to b to the x. It goes through this point 1. To graph the log function, what do? We draw a diagonal line. Okay, this is the line y is equal to x, and then we fold the graph, the green graph, about that line. Now this green graph, if you notice, it's asymptotic to the negative x-axis, right? If you go to this, so now when you fold it, it'll be asymptotic to the negative y-axis. Okay, and this point, which is 1, will come here. Okay, so the graph will go like this. So this is the graph of y is equal to log x base b. Couple things to note. Just like the exponential graph has a y-intercept of 1, the log graph has an x-intercept of 1. And if you remember, I already showed you that x always has to be greater than 0, not equal to 0 or negative. And you can see that the graph starts at x greater than 0. There's no graph for the log function for negative x values, or 0 for that matter. And those are some of the things we'll write down in a second, but I just wanted to show that to you right here. Okay, so to graph a log function is not that difficult. We just fold the graph of the exponential function about the line y is equal to x. Okay, so that's what the graph looks like. The other thing also to note about the graph function is usually exponential functions grow very rapidly, and since log is the inverse of the exponential function, it'll do the opposite. Exponential functions, log functions will grow very, very slowly. Okay, so they grow very, very slowly. For example, later on when we do use our calculators to find logs, you'll notice log of 1,000 is not a very big number. I can show that to you right now. Okay, just to prove to you that when x gets really big, let's say x gets 1,000, log of 1,000 is not a very big number. Okay, so let's say we take, I'll talk about ln in a second, but that's log 2. So let's say we take log of 1,000. You notice it's only 6.9. So it's a very small number. So log functions grow very, very slowly, Exponential functions grow very rapidly. Okay. Alright, so let's write down some of these properties of logs. And by the way, once we know how to graph one log function, we technically know how to graph a lot of them because of the graphing technique. So let me give you a couple examples first, so that way you can see some of the graphing techniques that we can utilize. So let's say they ask us to graph, okay, they want us to graph f of x is equal to log of x base 3. Okay. Alright, so let's do that. Now, before I do that, let me just point this one thing out to you. Let's say that in this, for the green graph, we had y is equal to b to the x. B was 2, so we have 2 to the x. Okay, what happens if x is 1? You'll get 2 to the 1, which is 2. Okay, so when x is 1, we'll get 2. So this point here would be, in this case, if it was b to the x, b is 1, we'll just get b. So if x is 1, we get b. So on the pink graph, what will that point become? Remember, it'll flip, right? So what will that point will become? It'll become b1, because x and y will switch roles. Okay, so whatever the base is, whenever x is the same as the base, then the value of y will be 1. So that's an important thing to note, because that gives you 2 points on the graph very quickly, this one and this one. So let's do that. Okay, all log graphs look like this, like the pink graph. So if they'd asked me, even though b is 3, if they'd asked me to graph this, I basically graph this. I just start a graph that looks, oops, should use the wrong color. I start a graph that just looks like my generic log graph. Here's what my graph looks like. So this is a graph of y is equal to log of x base 3. Okay, the only thing we're going to do is we're going to mark this as 1, and then that's one point we know because the x-intercept is always 1. What's the other point we also know? Well, let's think about that for a second. The other point we also know is, what did I just say? The point b1. Whenever the base is when x is the same as the base, that means if x is 3 here, if x is 3 and the base is 3, then the log of that is always going to be 1. So we can come over here, 1, 3. So we can go up here, this point is going to be 1. So we know 2 points, so we can just plot 2 points, and that gives us a nice graph of log of x base 3. Okay, so when you're graphing log functions, you can do them that way. If you don't like to do it that way, using just techniques of graphing, also let me do this one too before I show you another way to graph. Let's say if they want us to graph f of x is equal to, okay, they want us to graph, let's say, log of x plus 1 base 2. Okay, so let's think about this. What will this look like? Well, let me first start by drawing the generic graph. The generic log graph looks like this. If this is 1 and if this is 2, this point here would be 1. Why is that? So this is just my log y is equal to log of x base 2. Just when the base and the number are the same, when x is 2, base is 2, we know y is going to be 1. I showed that to you a minute ago. So I know this point. When the base and the number are the same, so when x is 2 and the base is 2, the y value is going to be 1. So we know this. This is a log graph of this. But I want to graph x plus 1. So I'm changing this x. Instead of x, I am taking the log of x plus 1. Anytime you change x, you do a horizontal shift, right? So we shift in the opposite direction of the sign. Since it's a plus 1, we're going to go to negative 1. Right now the asymptote is where? Because this is asymptotic, right? It gets closer and closer to this value, negative y-axis. You can see that. So right now the asymptote is y-axis. Okay, so that's going to shift because everything is going to shift by 1 unit. So this asymptote is going to go to -1, so I'll draw it with a different color. So this is x is equal to a -1. And this blue graph now is going to be asymptotic to this green line. Asymptotic means it's going to get closer and closer to. And this point 1 will also shift 1 unit to the left because of the horizontal shift, so this point will come here. This point will also shift 1 unit to the left, so it'll come here. Okay, so all these points are going to shift 1 unit to the left, so your graph is going to look like this. It's going to be asymptotic here, then it's going to go through this point. So there's a graph of y is equal to log of x plus 1 base 2. So you can see we can graph these functions by using graphing techniques now that we know the generic shape of the log graph. Okay, so just keep that in mind. Alright, the next thing we want to do then is, now that we know how to graph this, you can also, by the way, if you're not comfortable graphing this way, you can always change it to an exponential and graph it, but I'd rather you learn how to graph it this way. Okay. The next thing we want to talk about is properties of logs. Of the log function. And there are many properties of the log functions that you absolutely have to memorize if you want to get good with using log functions. So the first one is just the definition, okay, which states that if y is equal to log of x base b, then I can write it this way: x is equal to this base here. This base becomes the base of this number, so you get b to the y is equal to x. So if you have y is equal to log of x base b, then x becomes b raised to y. If you have this, you can write it this way. On the other hand, if you have this, you can write it this way. So basically what this lets you do is go from log to an exponent form, and this lets you go from exponent to a log form. Do you guys see that? It lets you go from between two forms. Let me give you an example. If you have y is equal to, I'm sorry, not y. If I have 4 is equal to log of 16 base 2, okay, this is using logs. What if I want to write it without logs as an exponent? Then whatever the base is out here becomes a base on this side, and then you just drop the log. So we get 2 to the 4 is equal to 16. Okay, so you can see that's what we have. Or another example, if you have an exponent, let's say I have 25 raised to -2 is equal to 1/5. Okay, so out here the base is 25, this is that. So if you look at this, we have this form right here. My base is 25, y is -2, and x is 1/5. So I want to write it as a log now. So what happens? You get y, whatever the exponent becomes is your y, so we get -2 is equal to, then you introduce log, so we get log of x, x is 1/5, 1/5 base b, b is 25. Okay, so in this case, this is my base, this is my y, this is my x, so we're using this, we're writing y, so my -2 is equal to log of x, so this is my x base b. So you should be really fluid going in these forms, okay, going back and forth. So that's the first property of logs. The second property is just information about the log itself, the domain. What was the domain of log function? What did we say? Earlier we said x had to be greater than 0, correct? So that is my domain. You can see I have no pink graph for any of these negative values of x or for 0. So that tells me that the domain of the log function is 0 to infinite. That is important to know because that tells me right away I cannot take log of 0 and I cannot take log of negative numbers. That's an important thing that will come across later. And the range of log is what? What is the range? If you go back to this graph, Range is for all the y values for which you have a point on the graph. So if you pick any y value here at the bottom, you'll always have a point on the graph, and if you have a point on the graph, you'll have an x value. That means there's some input that made that output. Same thing out here, this y value has a point on the graph, and so on. So the range basically is just from minus infinite to infinite. And you should have known this because in the last section we learned what? The exponential graph, the domain was minus infinite to infinite, and the range was 0 to infinite. That's what we learned in the last section about the exponential graph. Now, since the log graph is the opposite of the inverse of the exponential graph, the domain becomes the range, and the range becomes the domain for the log function. So we know that. Okay, so that's what happens. Okay. The next thing we need to know about log is the y-intercept, the x-intercept. For a log graph is always 1 and 0. So that implies one very important thing. If you take log of 1, if x is 1, and the base can be anything, then the log of that is always going to be 0. What is y going to be? 0. So that's the first very important property of log. Okay, because the x-intercept is 1, 0, that tells me log of 1 base b is going to be 0. And then there's no y-intercept to a log graph. You saw that it never crosses the y-axis unless you graph a log function that's shifted and so on. But the generic log graph doesn't cross the y-axis, it's asymptotic to it, but it never crosses the y-axis. So that's an important property, so please remember this one. Log of 1 is always 0. The next thing is, okay, as x goes to 0, as we get close to 0, as we keep getting closer and closer to 0, what are happening to the y values? They're getting smaller and smaller. They're getting smaller and they're going to negative infinite. Do you guys follow? As x gets close to 0, as we approach 0 here, the y values are getting smaller and smaller because that's an asymptote there. Okay, so in that case, this implies y goes to negative infinite, which implies y is equal, x is equal to 0 is a vertical asymptote, because whenever you approach a number and things blow up, we have a vertical asymptote, if you remember from the section on rational functions. Okay, and as x goes to infinite, this implies y goes to infinite. You can see that from the graph here. As x is getting bigger, as x is going to infinite, what is happening to the y values? They are also going to go to infinite, but they're going to go to infinite very, very, very slowly. Okay, so very slowly. Remember, I showed you that ln log of 1,000 was only 7 roughly. So that's something you should know about log functions. Okay. Now, and this basically, these two items only apply, okay, if b is greater than 1. Because if b is less than 1, then everything flips, and I'll show you that in a second. Okay, so let me do that, might as well while we are here. So we have, let's say we have y is equal to log of x base b. Okay, so if b is between 0 and 1, okay, then the log graph looks a little bit different than what we're used to. Okay, so in that case, the log graph looks like this. Normal log graph goes like this, correct? But now the log graph goes the other way. So this is still 1. So this is the graph of y is equal to log of x base b if b is between 0 and 1. If your base is between 0 and 1, so that's what's going to happen. So it's just going to be the regular log graph that's flipped about the x-axis. That's what it is. It's a regular log graph that's basically flipped about the x-axis. Okay. Alright. The next thing we want to do is, so we took a look at some properties of logs here. But these are out of all of these, just remember a few that are important. This definition is really truly important, so make sure you guys know that. Okay, oops. And then the other thing to note is this: log of 1 is always 0. Okay, so just remember those two things. So let's take a look at some more, lots and lots of more log properties. The other log property that I showed you earlier was this one. I showed you that when the base and the number are the same, if x is the same as my base, so for example, if I had log of x base b, if y is that, and if x is b, so we get what? Log of b base b, then we get 1. When x is b, we get 1, and you can see that, and I showed that to you up here actually, because when x is 1 on the green graph, what do we get? Let's do that again just to show you. When x is 1, we get y is equal to b to the 1 for the green graph, not the pink graph, the exponential graph. We get just b. So when x is 1, y is going to be, so that's this point. But so when we graph the log function, this point will become this point here, because you'll flip, x and y will switch roles. So y will become x and x will become y, so it becomes this point. So what does this point tell us? This point tells us that y is equal to log of x base, log of x base b, right? So what is y here? 1, and x is what? B. So that tells me that when the base and the number are the same, log of that is always 1, another very useful property. So let's write that down. When you have log of b base b, when the base and the number are the same, log of that is always 1. Okay. Next property of logs is the base property. So let's take a look at that. If b is equal to 10, if the base is 10, then we write then y is equal to log of x base 10 is the same thing as just log of x. So if there's no base given, it's assumed to be 10, and we call this the common log. Okay, and you'll notice that if there's no base given, that base is always assumed to be 10, just like with square roots. If you don't specify the index, it's always assumed to be 2, right? Same thing here. Okay, then there's another one. If b is equal to e, then if you remember the Euler's number, okay, then y is equal to log of x base b can be written as just ln of x. This is called the natural log. Okay, so these are the two logs you'll come across the most, and because you come across these logs the most, they have special notation. Okay, and also you have keys on your calculators for just those two. So like for example, you notice we have log key here, that means it's base 10, and then out here we have ln key, that means it's base e. Okay, so for example, log of 1000 is 3. You can see log functions grow very slowly. When x is 1000, y is only 3, and ln of 1000 is that. They're two different, because the base is different, you're going to get two different values. Okay, so just keep that in mind. So we have a natural log and a common log. Alright, 8. Well, if I only have two keys on my calculator and b can be any number greater than 0 other than 1, what happens if I have some other base? How do I find the log of that? So let's take a look at that. Okay, so if b is not 10 or e, and these are my nice bases, I usually call them nice bases, then I can write this. I can write y is equal to log of x base b, where b is not nice, it's not one of these. I can write it as ln of x divided by ln of b. The b comes here. Or I can write it as log of x divided by log of b. Out here the base is 10, out here the base is e. Okay, I'll come back and do an example. Let me just do a couple examples of these on the side so you can see. So I can see log of 5 base 5 is 1. So you can see those examples. And out here, if I take log of any number, doesn't matter what the base is. For example, log of 1 is equal to 0 because the base is 10 if you don't specify the base. Or ln of 1 is also equal to 0, the base is e. So those are two examples of that. So let me give you an example of this. Let's say someone wants you to find log of 5 base 2. Now this is not a nice base. So I can write it as what? ln of 5 divided by ln of 2. Or I can write it as log of 5 divided by log of 2. So these two are the same. So let's check that on a calculator. So I take ln of 5, close parentheses, make sure you do that, divided by ln of 2. We get 2.32 roughly. Then I can also do it log of 5, close parentheses, divided by log of 2. We should get the same answer. So if the base is not nice, we can still find the log of that. We just have to use something called change of base. This property is called change of base. It lets you change the base to base 10 or base e. Okay. Alright, let's move on. The next property of logs is this. Okay, it's a power property of log, which basically tells you that if you have log of some number x raised to n base b, then we can take that exponent and bring it in the front. So I can write it this way: n log of x base b. Okay, so here's an example of that. Let's say if I have log of x cubed, okay, base 2, then I can write it as 3 log of x base 2. I can bring that exponent in the front. That's a nice property of logs that lets you bring those exponents in the front. Property 10. Okay, if you have b, some base, this is an exponential number, raised to log of x base b. So if I raise b to a log expression that also has the same base as this, in that case we just end up with x. Here's an example of that. Let's say that if you have e to the ln of x, out to the base of ln is e. This is a log term, it's a natural log, so its base is e, this base is e, so we just get x. The next property of logs is this. We have log of m times n base b. If you're taking log of a product of two numbers, m and n, so what is that going to be? Well, that we can write this as log of m base b plus log of n base b. So we can write this product as a sum. This is called the product rule, or the product property. So this is the product rule for logs. It lets you write a product of a log as a sum. Okay, so the next property of logs is this. If you have a product property, you also have something called a quotient property. You can call it the product rule or the product property. This is the quotient rule or the quotient property, which tells you take the log of the numerator, base b, minus the log of the denominator, base b. So these are the product and the quotient properties. I just call them rules. Okay, so the next and the final property of logs is this. Okay, if you have, if log of, log of m, let's say log of m base b is equal to log of n base b. So you can think of normally y is equal to log of x base b, correct? So this you can think of it as y. Let's call this y1 since it's m, and this as y2. You can just think of it that because log is equal to y. Okay. So I have two different values, y1 and y2, since m and n are different, two numbers. Now keep in mind, log is also a one-to-one function, since because log is the inverse of an exponential function, so the inverse of the log function must be the exponential function. And you can see log is a one-to-one function. Doesn't matter where I draw a line, it only crosses the graph once. So what does that tell you? If log is a one-to-one function, that tells me that for each x, remember this is x really, okay, I can only have one y. So if these two log expressions are the same, if these two y expressions are the same, then these two x expressions must also be the same. So this implies m is equal to n. Okay, so when log of m is equal to log of n, that implies that m is equal to n. Okay, it's because of the one-to-one nature of the log function. Okay, so just keep that in mind. All right. So those are all the properties of logs, and I would strongly encourage you to memorize them, because the log properties are very, very useful, because our goal eventually is to solve equations where unknowns are exponent, or to solve equations that have logs in them. And without these properties, you're not going to be able to do that. Okay, so let's take a look at how to use some of these properties. Okay, majority of the time, for now, they're just going to give you some really trivial examples to just get you used to these properties, but eventually we want to do more stuff with that. Like I said, we want to solve logarithmic equations and things like that. So let's just use some of these properties. So first few examples are going to be changing from log to exponent form, and then from exponent to log form. I'll just give you two examples. I've already done that before, but let's do that. So let's say if you have y is equal to log of, I'm sorry, let's do this. Let's not use y. So let's say base 3 of 81 is equal to 4. Okay, so I have a log expression. I want to write this without logs. I want to write it as an exponent. And using the first property of logs, this is like your y, this is your x, this is your b, right? I told you what happens. This base becomes a base of this number. Okay, so this becomes 3 to the 4 is equal to, and then you just drop the log term, we get 81. So we wrote that as an exponent. Okay, on the other hand, if I have something like this, I have 10 cubed is equal to 1000. I want to write this as a log. This is an exponent. I want to write it as a log. This is my base, my exponent, we call that y, and this is x. So how do we write this? This base becomes the base on the log on this side, and the y just comes down. So we get 3 is equal to log of 1000 base 10. Okay, again, all we're using is property 1 that I gave you before. Okay, alright. The next couple examples are again just trying to get you used to properties. So let's say that they give you this. They give you log of x cubed square root of y divided by z squared, and they want you to write as separate log terms. That means they want you to write as log of x, log of y, log of z, separate log terms. So we're going to use the log properties. One of the properties I just gave you, number 12 and 11, are the ones we're going to use here, and also number 9. Okay, so I'll show you. The first thing you notice, I have a quotient. There's a quotient property of logs. So let's start with that. You take the log of the top, which is x cubed times square root of y, minus the log of the bottom. That's what the quotient property tells you to do. If you have the quotient, you take the log of the numerator minus log of the denominator. So we did that. Then if you notice, we have a product property. You have a product here, so I can use a product property. So this was property 12 that I just used. Now I'm going to use property 11, which tells me that if you have a product, write it as log of x of the first plus the log of the second minus log of z squared still. So we use the product property over here. Okay, Now we're going to use property 9, which tells me that if you have an exponent, that exponent can come in the front. So I get 3 log of x. Now this is square root of y. If you remember from the section on exponents and radicals, this can be written as what? 1 raised to half. So this is really a half here. The half can come in the front. So I get 1 half log of y minus 2 can come in the front, log of z. And there's your answer. They wanted us to write this as separate log terms, and we just did that. We wrote it as log of x, log of y, and log of z. Okay, so that's another example, and you can do different examples of this depending upon how complicated that expression is given to you. Okay, but the idea is still the same. All right, here's another variation of that example. Let's say they give us separate log terms. They give us 2 log of x minus 3 log of y minus 4 log of z. And now they want you to write it as one log term. So we are doing exactly the opposite of the previous problem. In the previous problem, they gave us one log term and they wanted us to write it as separate log terms. So we are doing the opposite. So we just basically do the opposite steps here. What's the last thing we did? The last thing we did was bring these exponents in the front, right? So the first thing we're going to do now is put those exponents back up. So this exponent can go back, this exponent can go back, and so can this. So I get log of x squared minus log of y cubed minus log of z to the 4. Then we're going to go from left to right and combine 2 log terms at a time. Because I have a minus here, that tells me that if you take log of something minus log of another thing, if you take log of something minus log of something, then you can write that as a quotient. You can see that. You can take the log of the first divided by the second. Okay, so that's what we're going to do since there's a minus in the middle. So I can take log of x squared divided by y cubed minus log of z to the 4. Again, I can combine these two. There's a minus in the front, so we're going to use a quotient property again. So we get log of x squared over y cubed divided by z to the 4th. Now I can clean this up a little bit. If you remember, if you have a over b divided by c, what is that? That is the same thing as a over b, right, using the division symbol, c over 1, because this is over 1. You can always change the division to multiplication. If I do that, what do? We flip the second fraction. So we end up with what? A over bc. So basically this denominator becomes the denominator of the big fraction. So this y will come down, so I can write it as log of x squared over z to the 4th y cubed. So we wrote it as a single log term. Okay, so that's how we do most of these problems. All we are doing is basically using log properties, and like I said, if you do not know the log properties, obviously it's very difficult to do these problems. So please make sure that you memorize those properties. I cannot stress that enough. I've already done that a couple times, but it's very vital that you do that, because without that you're not going to be able to do any of these problems. Okay, alright, and let me just do one last and then we'll move on. So we have 5 ln of x plus y minus 2 ln of y plus 8 ln of x. Okay, I want to write this as a single log term, so let's do that. You notice the first thing I'm going to do is get rid of these exponents, because once I get rid of these exponents I can use this product or the quotient rule properties, because if I have a difference of 2 log terms I can write that as a quotient. If I have a sum of 2 log terms I can write that as a product. Okay, so but to do that I have to get rid of anything that's in the front first. So let's do that. So I get ln of x plus y raised to 5 minus ln of y raised to 2 plus ln of x raised to 8. Then I take 2 log terms at a time and combine them. These two have the same base, which is e in this case. By the way, all of them have the same base, but they have a minus in the middle, so we can use the quotient property. So I can write it as x plus 5 to the 5th power divided by y squared plus ln of x to the 8. I can combine these two now. Because there's a plus in the middle, we'll use the quotient property. I get ln of x plus 5 to the 5th power divided by y squared times x to the 8th. And there's your answer. Okay, we wrote it as a single log term. So those were using some of those properties. Let's take a look at some other example. Let's say if they ask us to find this. Find the domain of the following functions. Okay, so I'll just give you a couple quick examples. So let's say if I have f of x is equal to ln of x plus 2. So I want to find the domain. Normally when we find the domain, what do we do? What have I showed you to do? Anytime you find the domain, we look for what first? We start with the assumption that everything works, and then we take out things that cause division by 0 and take out things that cause even roots of negative numbers. But in this section, in this case, what's going to happen here? Well, let's take a look at this. I don't have to worry about division by 0. There's no x in the denominator, there's no x in the radical. But remember, one of the requirements for log was what? What did we say? The domain had to be a positive, x had to be a positive number, right? From 0 to infinite. Or if you recall, when I defined logs, what did we say? X had to be greater than 0. Whatever I'm taking the log of, this had to be positive, because we can't take logs of negative numbers. So in this case, to find the domain, I'm going to have to do one additional thing. I'll want what we want. X plus 2 to be greater than 0. So we want x to be greater than negative 2. So the domain is all numbers greater than negative 2's. So not including negative 2, because it's just greater than negative 2. So this time we're not excluding numbers, we're trying to figure out which ones to keep. So because we can't take logs of negative numbers, we want this to be positive, so we're setting it greater than 0, and then we get x is greater than minus 2. Okay, here's another example. Okay, we want let's say if you have f of x is equal to ln of x over x minus 8. Okay, so what do we want? We want x over x minus 8 to be greater than 0, because we can't take logs of negative numbers. Okay, so let's take a look at this. This is a rational expression that is an inequality. If you remember way back in chapter 2, we did problems like this. The first thing we had to do was find the zeros of that. That is 0 when x is 0 and x is 8. We already have 0 on that side. If it wasn't, we had to move it to the left and simplify. And then what did that do? We drew this little sign chart. We put 0, 8. We drew lines. We put a factor. It's on the outside. X is 0 when it was 0 itself. So to the left, this x would be always negative. To the right, it would be positive. I hope you remember this from chapter 2. X minus 8 is 0 when x is 8. To the left, numbers are negative. To the right, they are positive, because if I pick any number to the left of 8 here, this expression is going to be negative. Like for example, if I pick 0, 0 minus 8 is negative. If I pick 2, 2 minus 8 is negative. On the other hand, if I pick any number bigger than 8, this will always be positive. I just want to know what sign each of these contribute, because depending upon what the sign of this is and this is, this whole sign will change. Okay, so when we multiply this, because we're taking this and dividing it by that, so if we take negative divided by negative, we get a positive, negative, and positive. Okay, so we wanted this expression to be what? Greater than 0. So that tells me if x is in here or in here, that would be greater than 0. So my domain is going to be what? All the numbers from minus infinite to 0, or, and we denote that by the union, all the numbers from 8 to infinite. So there's your domain of that function. Okay. And you can test it. Always check your answers if you're not sure. If I pick minus 5, for example, I take negative 5 for x, and then I have negative 5 minus 8. So I get negative 5 over negative 13. So it gives you 5 over 13, which is good because we want this to be positive. That's what it is. If you pick any number to the right, you know that's going to work too. Okay. So keep that in mind. I mean, any number to the right of 8. So you can always test these things. So that's how you find the domains of log functions. Okay. So that's pretty much it for that section. Let me just do one last example of change of base. I've already done one, but let's do one more. So let's say they want you to find log of 7 base 3. So I can write it as what? ln of 7 divided by ln of 3. Or I could have also written it as what? Log of 7 base log of 3. So if you do this on your calculator, we get an approximation since we are going to round off and stuff. So we take ln of 7 divided by ln of 3. We get 1.77. Okay, and that's the answer for that. Okay, so just keep that in mind. We can do problems like that, change of base. What I would recommend you to do is after you get done with this section, please take a few minutes and memorize these properties. They will absolutely make your life a lot easier. I forgot to mention one other type of problem in this section, so let me do that. And these are not in your homework sets, so please make sure that when you study for the test or the quizzes, you look at these problems, okay? So I like to ask these problems just because I like to test to make sure that you know your properties of logs. So let's say that if I give you this, okay, this is given to us, and these are just some random numbers I'm making up. They've told us that log of 2 base b is equal to 3. They've told us log of 3 base b is equal to 7, and log of 5 base b is equal to 11. So they've given us this too, okay? And they've asked us to find some of these things. So let's do that now. Because they didn't tell us the base, you cannot use your calculators to do this. So you have to know your log properties to do this. So let's start with something easy. Let's say they ask us to find log of 10 base b. But our goal is somehow we want to write this 10 as 2, 3, or 5. Okay, using algebra, like you can write it, 10 can be written as what? 2 times 5. So we want to do that. So let's do that. Anytime they ask you to find something other than what's given to you, you just ask yourself, how can I write that number as 2, 3, and 5? So in this case, I can write it as 2 times 5 base b. Then I can use the log property, which tells me what? If you're taking log of a product, you can take log of the first plus the log of the second. We're using the product property. And then we know log of 2 base b, it's 3, and log of 5 base b is 11, so the answer is 14. Okay, so that's what I want you to be able to do, because if I'd given you like 2 here, you could just punch this into your calculator and tell me what it is. But by giving you some random values of log of 2, log of 3, log of 5 base b, you're forced to use the log properties. And like I said again, these problems are not in your homework, so please make sure you guys come back and take a look at some of these. How about this? If they give us log of 3, actually let's make it interesting. How about log of 6 base b? Okay, now I want to write 6 as 2, 3, and 5, using 2, 3, and 5. But before I do that, let's take care of the radical, because I know that one of the things I can do with a radical is I can write it as an exponent. And there was a nice property of logs that lets us take this exponent and bring it in the front. So let's do that. I get half log of 6 base b. Now I can ask myself, how can I write 6 as using 2, 3, and 5? Well, that's easy, because 6 is just 2 times 3 base b. So I can write it as 1/2 Make sure you put brackets now because we're going to use a product property, so we're going to end up with a quotient as a sum. So we're going to end up with two terms, so you need to put brackets. If I don't put the brackets here, it looks like I'm only multiplying log of 2 by half. It's actually the whole thing. Then I get 1/2. I know log of 2, which is 3, log of 3, which is 7. So you get 10 divided by 2 is 5. Okay, here's another example, same thing. So these are really nice problems that test your knowledge on how to use the log properties. Okay, how about this? If I have log of b base, I have 15 divided by 12. Actually, let's make it not 15. Let's do 8. Let's do 15 divided by 8. Okay. Once again, I'm taking log of this. The only three logs I know are 2, 3, and 5. Okay. So let's rewrite this using that. But before I do that, since there's a quotient here, because our goal is to rewrite these numbers using 2, 3, and 5. But before you do that, always use log properties to simplify your problem. So I can rewrite this as what? 15 base this minus log of 8 base b. Okay. So now that we did that, okay, the next step is what? Well, the next step is try to write 15 using, we use the quotient property here. Try to write 15 as 2, 3, and 5. So I can write it as what? Did I do that before? No, we did 10. So 15 is what? 5 times 3 base b minus log base b of 8. 8 you want to write it as 2, 3, and 5. 8 can be written as what? 2 times 2 times 2. Or you can be creative and write it as 2 raised to 3. So that's what we're going to do, and then we're going to use a product property here again. So we get log of 5 base b plus log of 3 base b minus, oops, I forgot to do this, 2 cubed. So the 3 comes out base 2, because using the exponent property of logs you can bring it in the front. Now we know log of 5 is 11, log of 3 is 7, times 3 times log of 2 is 3. So we get 11 plus 7 is 18 minus 9, so we get 9. Okay. Alright, two more examples of this. Let's say we have log of 0.75 base b. Okay. So again, our goal is, if we cannot use log properties right away, then you ask yourself, how can I write 0.75 using 2, 3, and 5? So let's take a look at this. Is just basic algebra, math actually. 75 is the same thing as what? 75 over 100 if you move the decimal. And then you can reduce this. 25 goes into this 3 times and 4. I'm just showing you that because if I could have given you this, let's say if we had 0.15, that can be written as what? 15 over 100 again, and then you can reduce it. 5 goes into that 3 times and 20. Okay, actually let's do that. Let's make it 15. That'll be a little bit more interesting. Okay, so you can see you can always change a decimal to a fraction, so that's what we did. So let's do that. So we get log base b of 3 over 20. Since this is a quotient, I can take the log of the numerator minus the log of the denominator using the quotient property. I already know log of 3 base b, which is 7, that's given to me, minus, but 20 can be written as what? 4 times 5, and 4 can be written as what? 2 squared times 5. So that's what we're going to do. Make sure you guys put parentheses because of what's going to happen in a second here. Let me show you. So it's 2 squared times 5. Anytime you can write something as an exponent, always do that because there's a property of exponent that lets you bring it in the front. Now why did I put parentheses? Because now when you write this as a product, you're going to get two terms. Anytime you get two terms, you should always put parentheses just to make sure that you don't lose signs. We're using the product property now. I can bring this 2 in the front, so I get 7 minus 2 log of 2 base b, and I'll distribute this negative, so I get minus log of 5 base b. So I'm distributing this negative and also bringing this 2 in the front. So now what do we get? 7 minus 2 times 3 minus 11. So we get 7 minus 6 minus 11. So we get negative 10. Okay, so that's how we do some of these problems. We just want to be crafty enough to write the numbers in terms of 2, 3, and 7. And sometimes we might have to use some properties before we can do that. Out here we use a quotient property. One last example. How about this? Log of 24 base 3. Okay, so let's take a look at this example first. Alright, this is not b anymore, it's actually 3. So we'll worry about that later. Let's worry about 24 though. Okay, or actually let's do that right. Let's take care of 3 right away. You can do it either way. Remember, if the base is not nice, there was a change of base, and the change of base told us what? If you had log of x base b, you can write it as ln of x over ln of b, and so on. I can write it as, out here we wrote it using base e, but I can write using whatever base I want. So I'm going to write this as log of 24 base b divided log of 3 base b. The reason for doing that is because I do know log of 3 base b, so I wanted to use base b to write the change of base. Now 24 can be written as what? 24 can be in terms of 2, 3, and 5. It is what? 8 times 3, and 8 is what? 2 cubed times 3. So let's do that. So I get log of 2 cubed times 3 base b over 7, because log of 3 base b is that. And then on the top I can use the quotient, the product property. So I get 2 cubed times plus log of 3 base b over 7 using the product property. And then I get 3 in the front, so I get log of 2 base b plus log of 3 base b over 7. So you get 3 times 3 plus 7 over 7. 3 times 3 is 9. 9 plus 7 is 16 over 7. So there's the answer for that. So we did change of base out here. We were given some goofy base. We were able to do that. Again, similarly, if they'd given me this, find log of 2 base 5. I could have done it this way. I could have written it as log of 2 base b using change of base and log of 5 base b. The only reason why when we do change of base we use base e is because we have those keys on a calculator. Out here we're using base b because we do know the values of base b, of log of 2, which is 3, and log of 5, which is 11. So that's the answer. Okay, so these are some just extra problems that I always like to ask students on the test and on the quizzes and so on, just to check their knowledge of the properties. So please make sure that you come back and study this before you take the quiz or the test, because these are not part of your homework. Okay.